partially agree. Yeah,
Partially agree?
Because Molly had to work, but we usually have meets on Saturday.
Oh, so you didn't have a track? Didn't you guys have one on Friday?
Yes.
Okay. How did it go?
Right. Good.
Okay. All right. Was that like finals or?
It was Delco Chase qualifying was Friday, and Delco
Good. Fun times. All right, friends. So today is Unit 8 test review day, so that should be pretty fun for all of us. What I wanted to do today was basically go through really just two problems with you. I kind of want to do one of the gas type problems, right, which is what we learned on Friday, and then one of the solution stoichiometry problems, which is what we learned on Thursday, simply because it is, those are our like newest topics, okay, and we want to make sure that those things are really set in our mind. So let's go ahead and open up today's assignment here together. We'll kind of talk through it first, and then I will go ahead and do at least those two problems with you. If you would like to do more, I'm totally open to that. You guys know I'm down for whatever, but you just have to let me know. So before we take a look at this, yes, I am recording the meet. Yes, thank you for your reminder. So let's talk a little bit about your test. I was just finishing it up this morning. I hadn't decided yet what I wanted to do, but what I did want to do was make it so that it could be done in class. So I cut it down to the 5 questions. There is a 6th question, which is an extra credit question. I can't remember what class it was, but somebody asked for extra credit on the test, so I am obliging. So there are 6 total questions, but the last one is extra credit, okay? What should you expect to see on the test tomorrow? They're all going to be stoichiometry questions. There's just no way around it, right? I'm not going to waste your time with like simple, not involved questions, right? So you should expect to see a conversion question, right? So that could be grams to moles, it could be grams to grams, it could be moles to grams, whatever. Okay, you're probably going to opt for the traditional stoichiometry for that one. You should expect to see a limiting reactant problem. You guys know that that's a big deal. You just took a quiz on that last week. Hopefully you looked at my feedback on your quizzes and you are confident with those that process. You should expect to see a solution stoichiometry question. So what does that mean? That means you're going to have to use that molarity equals moles over liters formula at some point during that question. That's one of the types of questions I want to review together this morning. You should expect to see 2 gas questions. One of the gas questions is going to be at STP. At STP, we use that 22.4 liters per 1 mole conversion. Then you should expect to see a gas problem that is not at STP, so you have to use that PV equals nRT equation, okay? Last but not least, the extra credit question, I'll tell you, is similar to the lab question that you're going to see on your test review. The reason why I am making it extra credit is because obviously you haven't done the lab, but if you can do the lab question on the test review, you should probably be able to do the test question on the lab data. Okay, it's really just a straightforward stoichiometry. The only thing is you have to read the problem and kind of, get the info from it. Okay, is there any question about, are there any questions about that test format for tomorrow? You guys know the drill. You're going to have to upload your work into an assignment after the test. So we're pretty used to that at this point in time. All right, so there's a bunch of bullet points at the top of the page that tell you like what's on the test. You don't really have to spend too much time on that one. All right, so the first problem is just a really good question. It kind of goes back to that visual of limiting reactants. Remember, that's how we actually started learning about limiting reactants. So that's question kind of number 1. Questions 2, 3, 4, and 5 are all conversion questions, okay? I will tell you number 5 is a limiting reactant problem. So if you're like looking to start with the limiting reactant problem because you still feel like a little nervous about the limiting reactant problems, then I would say start with number 5 because that's your limiting reactant problem in this test review. All right. there's your lab data question. We can kind of come back and do that one too if you think that would be helpful. It probably would be helpful, so let's plan on doing that after we get through our gas and our solution problems. Okay, they're labeled down here, so I'm down to question like 7. You are going to be given your 22.4 liter, your molar volume there. You've got your PV equals nRT, and you've got your R values. Okay, I told you before, I don't expect you to memorize those. I don't expect you to memorize those. Okay. All right. So let's go ahead and tackle question number 8 together. All right. So let's read this out loud. Nitrogen gas, hydrogen gas, bless you, combine to produce ammonia gas. So you guys know the drill. Let's go ahead and write out our balanced chemical reaction first. All right, and then we'll go ahead and balance this one. I think it's 1, 3, 2. All right, so let's kind of figure out what we are asked to find and what we are going to begin our problem with. The first thing that I notice is that those 3 letters STP, okay? As soon as I see that, I should be thinking at some point during this problem, I'm gonna have to use the 22.4 liters per 1 mole, all right? I'm not going to try to trick you, all right? If it says STP, you are going to have to use your 22.4 liters per 1 mole, all right? So it says what volume of hydrogen gas, so we're gonna try to find liters of H2. Okay, remember volume for gases is always going to be, volume for gases is always going to be liters. Okay. At STP would be required to react with 10.0 grams of nitrogen gas. All right, so I'm going to start my problem, bless you, with 10.0 grams of nitrogen gas, the N2, and somehow I'm going to have to get to volume of H2. So I'm definitely thinking we're going to use a little bit of stoichiometry. We're probably going to use a molar mass here. And then, bless you, I already know that I'm going to have to use that 22.4 liters per 1 mole. Okay? So let's start off with what we're given over 1. Okay, now remember, we're trying to get to H2. In order to get from N2 to H2, or from one reactant to another reactant, okay, in any problem, I have to get it to moles, all right? So what that tells me is I need the molar mass of N2 to start this problem. Molar mass of N2 comes out to be 28.01 grams per mole. So I'm going to go ahead and put that in the denominator so that my units cancel. One mole N2 on the top. We know that's the definition of molar mass. All right. If I stop my problem right there, I would have moles of N2. I don't want moles of N2. I want liters of H2. All right. So I'm going to go ahead and use my mole ratio next to get from N2 to H2. So I'm going to have moles of N2 on the bottom so that my units cancel, and then moles of H2 on the top. Okay, I'm going to look at my balanced chemical equation. There's a 3 coefficient in front of the H2, and there's a 1 coefficient in front of the N2. That's how I get my 3 and my 1. Last but not least, we want volume, we want liters. So I'm going to use my 22.4 liters of H2 is equal to 1 mole of H2, so that's going to go on the bottom so that my units cancel. All right, how do we feel about setting up this type of problem? Pretty okay, Archie?
Yeah, I was one thing that I forgot to do the liters thing, but I was thinking that you had to do that separately. I don't know why.
You can totally do it separately. Absolutely. If you want to solve for the moles of H2, like, basically stop before you get to, adding this guy in, you can totally do that. There's nothing wrong with that. Absolutely. Okay, fantastic. So we should end up with 3 sig figs in our answer because 10.0 has 3 sig figs, and I think I end up with 24.0 liters of H2. All right, so there's gas problem number 1, right? At STP, we are going to have to use our 22.4 liters per 1 mole. Any questions or concerns at all, guys? Everybody's okay? All right, so let's check out number 9 next. All right, number 9 says, consider the following reaction. Aluminum oxide decomposes into aluminum metal and oxygen gas. Okay, so let's write out our reaction first. So aluminum oxide. This compound always throws people off. I think it was actually in your quiz last week, aluminum oxide. Aluminum is +3, oxygen is -2, so you end up with Al2O3. I don't know why that gets people sometimes. All right, so it says it decomposes. So here's my arrow into aluminum metal, so Al solid, and oxygen gas. All right, so let's see here. We're gonna need to get the oxygens up to 6. So let's put a 2 and a 3, and then we need a 4 on the aluminum. So 2, 4, 3 on my phone. All right, so let's see what this actually says. It says, what volume of oxygen gas? Okay, so they want volume of oxygen gas. So volume is liters of O2. And what have they given us? All right, they've given us 32 degrees Celsius, which I'm going to go ahead and turn into Kelvin by adding 273 to it. Okay, so I get 305 Kelvin. They also give us 0.975 ATM, and they give us 4.32 grams of aluminum oxide. Okay, so if I were to take a look at my PV equals nRT, all right, if you are lost in the sauce, all right, you write down your PV equals nRT, you're like, okay, let's see what I have. I have temperature, all right, I always have R because it's a constant, it's always known. I don't have N because I don't have any moles here. I don't have volume because that's what I'm solving for, but I do have pressure, okay? So what you should notice is you have volume and you have N. You have 2 unknown variables, which tells you you cannot begin this problem with PV equals nRT. All right, the only other option, if you can't begin that problem with PV equals nRT, the only other option is to begin it with stoichiometry. Now, they give us 4.32 grams of Al2O3. So do you think it's possible to convert my 4.32 grams of Al2O3 into moles of O2 so that I can use that in my PV equals nRT? Because then I'll only have one variable, it'll be volume, and that's actually what I'm trying to solve. All right, so let's go ahead and begin this problem by converting my 4.32 grams of aluminum oxide to moles of oxygen gas. Okay, I'm gonna start with my 4.32 grams over 1. I know I'm gonna need my molar mass of aluminum oxide in the denominator here. Molar mass of aluminum oxide is 101.96 grams per mole. Okay, I can go ahead and fill that in. Now remember, just like we worked in the problem before this, we're trying to get to the same, end goal. We're trying to get from one component of the balanced chemical reaction to another component. All right. So I'm going to go ahead and use my mole ratio because I know I need to get to my O2. All right. So I'm going to have moles of Al2O3, so my units cancel. And then I have moles of O2 on the top because that's what I want. So I get a 3 here and I get a 2 here, right? Because those are my coefficients. Now, can I stop or do I have to keep going? I can stop, right? Because if I stop, look at the units. Grams go away, moles of Al2O3 go away, and I'm left with moles of O2, which is what I want for my PV equals nRT. All right, so I can solve now. Keep with the sig figs. All right, we're looking for 3. When I multiply this out, divide this out, I get 0.0636 moles of O2. Okay, everybody with me so far still? All right, so now if we go back to look at our PV equals nRT, we've got that N value. Okay, now we're going to be solving for V. All right, so if I rearrange this equation, I'm going to get V equals nRT over P, okay? Because to get that V by itself, I have to divide both sides by pressure. All right, you guys know I like to rearrange first. If you like to plug it in and then rearrange, that's totally fine as well. Both methods will get you to the same place. All right, so let's plug in all of our values now. So volume equals number of moles. We just calculated that 0.0636 moles. Our R value, how do we figure out the R value again? It's a constant, good. And what is it dependent on? Because we actually have 2 R values. We have the 0.0821 and we have the 62.4. What unit do I need to look at, John? The ATM. So because my pressure is in ATMs, I'm going to opt for the 0.0821. Okay. And then temperature, we already converted that, right? It's 305 Kelvin. All right, all divided by pressure, which they gave us 0.975 atmospheres. All right, sticking with the 3 sig figs here, we should have 3 in our answer. And that value comes out to be 1.63. And remember, guys, we need a unit liters of O2 on there. All right, how do we feel? Good? All right. Guys, the reason behind me talking through, like looking at PV equals nRT and figuring out, okay, we can't start with that. That's the thought process I expect you to have when you go through these problems, right? I don't need to think through that process, right? I've been doing these problems for like over 10 years. But that should be the thought process that I want you guys to take, okay? Being that this is your first time through with these problems. All right, questions or concerns on gases? Anything on gases? Everybody's okay? All right, let's take a look at, I want to do solutions with you again. Okay, I think the only solutions one I put on here is number 11. I think, yeah. All right, so let's tackle number 11. They give us the reaction, that's cool. It's already balanced, that's even cooler. All right, let's see what this problem says. It says, what mass of calcium carbonate is needed to make 1.2 liters of a 1.7 molar calcium carbonate solution? Okay, holy cow, we've got a lot of stuff going on here. So first off, let's remind ourselves, molarity equals moles over liters. All right, so this problem is they're asking us for grams, right? What mass? That's grams. So let's see, we're given molarity, okay? We're given liters. Can we find moles then, and then use the moles to get to grams? We can, all right? Let me go ahead and rearrange my equation. So it's going to come out to be moles equals molarities times liters, okay? And then I can go ahead and plug in my values there. My molarity is 1.7. My liters are 1.2. Okay, and then this is going to give me moles. Just quick multiplication there. I really get 2.0. Suspect. Let me verify my math, guys. I get 2.4. Okay, 2 sig figs, yeah, it does come out to be 2.0. So guys, that's moles of the calcium carbonate, which is that CaCO3. All right, now just remind yourselves here, they do ask for mass. How do I go from moles to mass? I'm going to use my molar mass. Okay, so let's go ahead and set this up here. Actually, I can just kind of do it in one big line here, right? So we can put that over 1. And then we've got 1 mole of CaCO3 in the bottom. We're going to have grams of CaCO3 on the top. We're going to need our molar mass of that calcium carbonate. All right, and I should get a molar mass of 100.09 grams per mole. So on top, I'm going to plug that value in. All right. So I'm going to multiply straight across the top. I should stick with my 2 sig figs. Because of that, I end up with an answer in scientific notation. I end up with 2.0 times 10 to the second grams of CaCO3. All right, we'll throw back with scientific notation there. All right, everybody with me so far still? All right, part B, what volume of 3.0 molar hydrochloric acid is needed to completely react with the amount of calcium carbonate in part 12A above? Oops, it's supposed to be 11A. That's my bad, guys. 11A. Okay, so, holy cow. Let's see what we need to do here. We need a volume for hydrochloric acid. Molarity equals moles over liters, right? We are only given here the molarity. They want us to find the liters, and this is all for HCl. So if I were to try to find liters, I would have to get the moles of HCl. How do I get the moles of HCl? Well, can I use the values from part A above to do some stoichiometry? You are probably thinking yes. All right, so if I take my 2.0 moles of CaCO3, can I convert that to moles of HCl and then have that value that I need to solve for my volume? I think we can. All right, so let's do it. So we've got 2.0 moles CaCO3. We just need to get some moles of HCl. So this should be a pretty quick conversion, right? Just a mole to mole. So we're gonna have moles of HCl on the top, moles of calcium carbonate in the denominator. Okay, I'm looking at my coefficients. We've got a 2 in front of the HCl, a 1 in front of the calcium carbonate. So this comes out to be 4.0 moles HCl. All right, now we've got moles. They gave us that molarity of 3.0. So now I'm ready to go back and use my molarity formula. Okay? If we rearrange to get liters, we're going to end up with liters equals moles over molarity. So I'm going to go ahead and plug in my values now. Moles, we just solved for 4.0 moles. Molarity, they gave us 3.0 M. So liters is going to come out to be 1.3 liters of HCl. Careful there, okay, because we are dealing with the HCl. Yes, Tyler. Yeah, go ahead. All right. So I have a little bit of bad news for you. The rest of this question, well, part C, I should say, is actually a limiting reactant problem. A limiting reactant problem. I know. Life is so hard. I'm sorry. All right, I promise tomorrow you only have to do one limiting reactant problem for me on the test. All right. What? There is just a normal limiting reactant problem on the review. Yeah, that was number 5, I think it was. Yeah. Okay. Well, we're going to do it together, so it's fine. It's all good. All right. You guys sound so enthusiastic. Okay, it's not that bad because, look, we already have our moles, okay? We've got our moles of calcium carbonate, and we've got our moles of HCl, all right? So let's come down here. Let's make our BCA table. This is good practice. It really is. I know it seems like torture, but it is good practice. Bless you. All right, so I'm just going to rewrite my equation here real quick. All right, and let's see. We're not asked about anything except for grams of water. So for my carbon dioxide and my calcium carbonate, or I'm sorry, calcium chloride, we're just going to be able to squiggle those guys out. Oh, 1 for the H2. Yes. All right. So we can get rid of this guy. We can get rid of this guy. We already have our values to begin with, right? So we had 2.0 moles of the calcium carbonate. We had 4.0 moles of HCl. And you know the drill. We always start with 0 moles of product. All right, so let's go ahead and figure out what our limiting reactant is. Excuse me. I'm going to start with my 2.0 moles of calcium carbonate. Okay. Try to get that to HCl. Two 2.0 times 2 gives me 4.0 moles of HCl. Here's your favorite question of the day. Oops. Do I have at least this amount? I do. I do. All right, cool beans. This is a little bit strange, right? Because look what's going to happen. Do you recognize what's going to happen? This is going to be our limiting reactant, calcium carbonate, which means HCl is our excess reactant. But what do you notice about the value for HCl? It's going to be 0 after, right? So this is a unique problem in that kind of, I don't want to confuse you, but kind of, both of your reactants get all the way used up, okay? Which is not a very common occurrence, right? All right, so to get our change value for my water, all right, I end up with, is everybody okay if I fill that in with a 2.0? Okay, and then 2.0 moles of water in my after. All right, last step here, friends, is to get to grams, okay, because they want mass. So I'm going to take my 2.0 moles of H2O and convert that into grams. That shouldn't be too bad. Okay. Molar mass of water is 18.02. All right, so plug that in on the top. We end up with, keeping the 2 sig figs here, guys, 36 grams of H2O. All right, questions, concerns, thoughts or feelings, anything at all?
I had a question about like how the all like when you subtracted the 4.
Mm-hmm.
So I know that the CaCO3 is the limited reactant,
Mm-hmm.
but would HCl be a limited reactant? Would they both be limited reactants, or would it just still be the one?
So technically, because we are using up all of the HCl, it would be a limiting reactant, right? So you could label them both as limiting reactant. I will be very honest with you. I'm not going to give you a limiting reactant problem on your test tomorrow where you find this situation, right? So it will be very obvious to you tomorrow which one of your reactants is, going to be limiting, and that's the only one that's going to be all the way used up. Any other questions? No? Everybody's okay? All right. Say again? Yeah, yeah. No worries. Can you see it okay? All right. Good, Archie?
No.
Oh, you still can't see it? What part do you need to see? This one? Or the other side?
Oh, no, I just didn't have enough.
Oh, okay. You got it? Good? All right. Guys, do you want to do the lab problem together, or do you think you can handle it on your own? Separately? On your own? Okay. Let me go ahead and just point one thing out, and then I will let you guys do it on your own. Probably the hardest part of this is literally dealing with the 4 numbers that they give you, because you do have to do like a little bit of manipulation with the numbers. So let me just do a little bit of work for you. I'm gonna tell you that this subtraction gives you 21.6 grams of Pb, which is lead, and this is your actual yield. And then I'm going to tell you that this subtraction, 6.50 minus 3.86, gives you 2.64 grams of magnesium. And this is the value that you should use to go to grams of PV. All right, obviously you still need to write your balanced chemical reaction there. This problem is a straight percent yield problem, okay? The only thing that's different for us that might be a challenge is what I just showed you. Looking at that lab data, being able to say, okay, massive beaker plus lead, if I subtract those two amounts out, that's gonna give me my massive lead by itself, okay? And then being able to say, okay, before the reaction, I started with 6.5 grams. After the reaction, I have 3.86. If I subtract those, that's gonna be the grams of magnesium that I used during the reaction. All right, not a super like challenging lab problem, but just a little bit different than what we've seen so far. All right, any questions or concerns, guys? All right, get this done, guys, please. Do not wait until like midnight tonight to work on this, okay? Give it your best effort. All right, your test is gonna be tomorrow, okay? There's no extensions on that, so you gotta get this work done, get prepared for that. All right, if you have a question or concern, I'm gonna leave the Google Meet open, you know the drill, but you can always reach out to me via Canvas as well. All right, virtual friends, have a wonderful rest of your day, and I look forward to seeing you guys tomorrow morning.
What's the grams of magnesium?
So you're gonna take the grams of magnesium and go to grams of PV to get your theoretical yield. But you have to write your chemical equation first. Whoops.
Miss Link.
Yes, go ahead, hon.
So